Hello everyone. In part 14, that is the previous video, we had introductory idea of aldol reaction, which is basically where the nucleophile is carbonyl based. Today we will talk about application of this reaction and also some problems. But before watching this video, I will suggest you to watch the previous video, that is part 14. So it will be convenient to understand all the aspects of this reaction in this video, okay? And for that video, you can click on the link appearing on the screen. So first is the application part. This is our aldol product, which is beta hydroxy carbonyl. This is alpha, this is beta. At beta position we have OH group and CHO group. Now these two groups are very such that we can convert them to some other compounds. So that is why this starting from aldol we can make variety of compounds. Now the next step, that is in presence of acidic medium, though in basic condition also the dehydration step that is possible, that we have already seen in the last video. So here I have written H plus, and this is the dehydration step. We have to heat for removal of water molecule. Now we are getting alpha beta unsaturated aldehyde. Next, if we reduce it with hydrogen and hydrogen in presence of palladium on charcoal, then CC double bond, that will be reduced to CC single bond. So now it is saturated aldehyde. Okay. Next, we are using sodium borohydride reducing agent. So here the CHO group, that will be converted to CH2H. Now we have two OH group at 1 and 3 position, so that is why it is 1,3-diol. Now another reducing agent, lithium aluminium hydride. If we are using it on this alpha beta unsaturated aldehyde, here CHO group will be converted to CH2H. Now normally NaBH4 we also can use, but why we are using lithium aluminium hydride? Because if we use sodium borohydride, then there is a chance that CC double bond, that will also be reduced. Normally if CC bond, it is not present adjacent to any carbonyl group, under that condition sodium borohydride cannot reduce CC double bond. But if it is close to CO, that is carbonyl group, then it can also happen with lithium aluminium hydride, but the chance is less. It is mostly with sodium borohydride when we have any alpha beta unsaturated carbonyl compound in presence of NaBH4. Now this CC bond, it is also prone to reduction only in presence of this carbonyl group adjacent to it. So that is why we are not using sodium borohydride, and this that is sodium borohydride and lithium aluminium hydride, that I have discussed in part 10 of the same topic, that is nucleophilic addition to carbonyl. So please watch that video. You can click on the link appearing on the screen. Fine. So here we are using lithium aluminium hydride to reduce only the aldehyde, not the CC double bond. Another reducing agent, hydrogen in presence of nickel. Now this reducing agent, it will reduce both the CC double bond as well as the aldehyde. So as a result, we are getting saturated alcohol. So in this scheme, you can see starting from aldehyde, we are first getting beta hydroxy carbonyl compound, then in presence of sodium borohydride 1,3-diol, and dehydration step that we have already seen in the last video. Different types of reducing agent we are using, and we are getting different types of product. So depending on the requirement, which type of product we actually want to get, we have to choose our reagent accordingly. Fine. So this is another application. This is basically intramolecular aldol, and intramolecular aldol can be used to close 5 and 6 member rings. Here we have taken this diketo compound, and this is symmetric in nature. Fine. So here if carbonyl is generated here, now carbonyl, it will be generated at the terminal this carbon. The reason is, if it is generated at this carbon, then the ring size, that is it will attack here, and the ring size will be 1, 2, 3, 4 membered, which is not stable at all. So that is why this is the first reason that negative charge will be produced at the terminal CH3. Another reason is this this hydrogen that is more acidic, because if the carbanion is generated at this carbon, then because of this CH2, you can consider it as alkyl part, it will have some plus I effect. So that is the reason these hydrogens are less acidic. So this negative charge, it will attack here, and if we number the carbon 1, 2, 3, 4, 5, 6, so it will be 6 membered. Okay, so number will be 1, 2, 3, 4, 5, 6. So first at 6 position there will be OH group, C double bond O, it will be converted to OH, and then there will be removal of water. So this is also alpha beta unsaturated carbonyl compound. Next example. Now this molecule is not symmetric. In the left hand side we have ketone, but right hand side we have aldehyde. Okay. Now carbanion will be generated first, and this carbon will be generated here, because if it is generated here, then the ring size will be 3 membered, which is not stable at all. So this negative charge, it will attack this carbonyl carbon of aldehyde. So here the aldehyde is the acceptor. Okay, this is electrophile. It is acting as electrophile, and the left hand side, that is acting as nucleophile. So ring size will be 1, 2, 3, 4, 5. Here first there will be generation of OH, and after that there will be removal of water. So this is number 1, 2, 3, 4, 5. Okay, you can compare the number. Always for this type of reaction, it is always do the numbering so that there is less mistake. Okay. Last example, this is also symmetric. Now any side you can generate the negative charge, it doesn't matter. So if it is generated here, it will attack at this carbon. This is 1, 2, 3, 4, 5, 6, 7. So this is 1. Okay. This is 2, 3, 4, 5, 6. And attack is at 7 carbon. So this is 7. Fine. So this CHO, it will remain intact, and here the right hand side is acting as nucleophile, and the left hand side, that is acting as electrophile or acceptor. Fine. So in this way we can make 5 or 6 membered ring by intramolecular aldol reaction. Now we have some problems. Explain the observation. So here we have taken this unsymmetrical ketone compound, and another molecule is aldehyde, and here we do not have any alpha hydrogen. So the enol, that is the nucleophile, it can be formed only from the ketone compound. Suppose this is A, this is B. So our nucleophile, that is a donor, that will be generated only from A, because B is non-enolizable. Fine. So when it is acidic condition, first there will be protonation of this oxygen. Now enol can be formed either by removal of this hydrogen or this hydrogen, because there are two different types of alpha hydrogen. So if the left hand side hydrogen is removed, the enol will be in presence of H2O, it will capture this hydrogen. Okay. And if the right hand side hydrogen is removed, then the product will be like this. Now among these two enol, if it is 1 and this is 2, which one is more stable? Obviously 2 is more stable compared to 1. Now why it is so? Because this is more substituted alkene, but this is less substituted alkene. Why it is more substituted? Because we have 2 alkyl substituents. Here we have only 1 alkyl substituents. Another point is that here we have total 3 alpha hyperconjugable hydrogen. If we consider, we have total how many hyperconjugable hydrogens? Total 6 hyperconjugable hydrogens. But in case of one enol, there is only 2 hyperconjugable hydrogens. That is why 2 is more stable than 1. Now the next step, this is very known step. So basically the final compound, if I write, that is after removal of water, then it will be so this is basically this product. I have written in a different way, but actually this is the same product. Okay, so under acidic condition, it proceeds via the enol tautomer, and the more stable of the 2 enol tautomer is that with the more substituted double bond, that is 2, not 1. From 1 also there will be some product, but it will be major product under acidic condition. And under basic condition, what happens? Now we have to understand the stability of the enol in terms of acidic hydrogen. Fine. So here, which hydrogen is more acidic, that we have to see. These 2 hydrogen or these 3 hydrogen? Which one is more acidic? Obviously this side hydrogen is more acidic. The reason is because here we have this CH3 group which will have some electron donating effect. That is why these 2 hydrogens will be less acidic. So base catalyzed reaction proceed via an enolate anion donor species, and the kinetically favored proton removal is from the less substituted alpha carbon. So this will be fast, that is proton removal from this carbon, that will take place fast, because now it is basic condition. So that is why we are considering the acidity. In case of acidic condition, we have not considered acidity. Then we have considered the stability of the CC double bond in the enol. But here we will consider the acidity of the alpha hydrogen. So if this hydrogen is more acidic, the HO minus, it will capture this hydrogen, and our enolate, this is actually enolate because O minus is there. That is the difference between enol and enolate. If in enol the OH is O minus, then it is enolate. And next pH, CHO, attack will be from this CH3, that is carbonyl is basically here. So first we will get OH, and finally there, sorry, this is CH2, CH3, and finally there is proton removal. So we are getting this product, this OH and H will be removed. Okay, so this is the reason why under basic condition and acidic condition we are getting 2 different types of product. This is not exclusive, but it will be major product. Okay, we have to predict the products. Here we have taken 3 molecules of formaldehyde and 1 molecule of acetaldehyde, and the basic medium that we are using, this is not very strong base like NaOH or KOH. Okay, so first all these 3 hydrogens of CH3, all these are alpha hydrogen, and donor will be this species. This will be accepted because there is no alpha hydrogen. So enol can form only in acetaldehyde, and all these 3 hydrogens will be removed one by one, and formaldehyde, that is CH2OH, that will come from formaldehyde. So we will get 3 CH2OH attached to this carbon. Basically 3 times the reaction will take place, and here what we can do, as it will generate the enol, we can add it slowly to the formaldehyde so that there is no self-condensation, self-aldol between 2 acetaldehyde molecule. That we have already discussed in the last video, that how to control this cross-aldol product, because we want to get one product as major. Fine. And this is CH. Now in the final compound there is no alpha hydrogen, but there is aldehyde, right? Now we may think that there is a chance of Cannizzaro reaction, but actually here Cannizzaro will not take place because Cannizzaro and aldol condition is almost same. But remember, for Cannizzaro compared to aldol, more drastic condition is required, and here we are using very mild condition. We are not using strong base. Sodium carbonate we are using. That is why Cannizzaro reaction that will not take place, because this molecule is such where it is not enolizable. There is no alpha hydrogen, and the necessary criteria for Cannizzaro reaction is the absence of alpha hydrogen. So in this molecule there is no alpha hydrogen, but still there will be no Cannizzaro because the condition is mild. Okay, so Cannizzaro also I have discussed. For the related video, please click on the link appearing on the screen. Fine. Next example. And one thing I will also mention here, that suppose if we are using NaOH or KOH in this reaction, then what will happen, that I will mention here. So what will happen then? Then this molecule, it will react with another molecule of formaldehyde. And obviously if you compare these two aldehyde, if this is A, this is B, B is more reactive because it is formaldehyde. So first the HO minus, it will attack here. There will be formation of O minus OH. Now hydride will be transferred to this aldehyde. So this hydrogen hydride, it will be transferred here. Sorry, what I'm saying, it will be transferred at this carbon, at this carbonyl carbon, and as a result we will get product. This is CH2OH, 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 and here we will get another CH2OH. Okay, by the hydride removal from this anion. Okay, and the fate of this molecule is it will be converted to formic acid. So it depends what type of condition we are using. So if it is NaOH KOH, then first there will be crossed aldol. So this is crossed aldol, right? And when you are getting the crossed aldol product, then there is cross Cannizzaro reaction, because both in aldehyde A and B there is no alpha hydrogen. That is why Cannizzaro can take place. But remember, dilute Na2CO3 if we take, then reaction will stop here. Okay, next example. Now we have taken nitromethane, not two molecules of carbonyl we have taken. We have taken one carbonyl compound which is benzaldehyde and nitromethane. So basically, as it is carbanion generation, so here also carbanion can be generated by removal of one hydrogen. So it will be CH2NO2. Okay, so this is also analog of aldol, we can say. This negative charge, it will attack here. So first there will be formation of OH NO2, and as there is another hydrogen, if we heat it, I am writing here the heat sign, then removal of water, and we are getting PH CC double bond NO2. Fine. And the next one, again we have taken one aldehyde molecule, another molecule, there is active methylene group, that is acidic hydrogen is present. So carbanion we can generate, just like this. Here we have generated the carbanion. So first there will be generation of PH CH2 minus Cn. This negative charge will attack here. One hydrogen, so this hydrogen and this OH will be removed. So finally we are getting okay, this is the final product. Now we will work backward to derive the starting carbonyl compound. You can also consider it as retro-aldol, because the molecule that is given, that is actually alpha beta unsaturated carbonyl compound. So which is the final aldol condensation product. Okay, so we can work backward, and as this reaction is reversible, so under standard condition, that is if we can manage the condition properly, then we can get back the original carbonyl compound, that is the starting carbonyl compound. So it can also be considered as retro-aldol. So first what we will do, as our addition product is beta hydroxycarbonyl compound, and then there is condensation. So the molecule that is given, that is already condensation product. So first we will generate at beta position, we will write OH. So H3C, OH, CHO and CH2CH3. Next what we will do, we will, this OH we will convert it to carbon. So we can make here, sorry, let me write it clearly. So this HO bond will be broken, and the two carbonyl compound, so CH3, 2 carbon, then aldehyde. And from this side, actually both are same molecule. Okay, so two molecules of CH3, CH2, CH2, CHO. So this is actually self aldol, because two aldehyde molecules are same molecule. Next example, this is also alpha beta unsaturated carbonyl compound. First we will generate OH at beta position, and we will remove the unsaturation. So this OH bond will be broken, CC bond will be broken. So from this side we will get cyclohexanone, there will be hydrogen, and here also we will have, actually this is also same molecule, this is also self aldol reaction. Two molecules of cyclohexane, hexanone, two molecules of cyclohexanone. This is alpha, this is beta. At beta position we will write OH. So this OH bond will be broken, this CC bond will be broken. So what we are getting, Me3C, then CHO, and from the right hand side we will be getting acetaldehyde. Now the two molecules, they are not same. Okay, so one molecule is non-enolizable, this is non-enolizable, so it will act as acceptor, and it will be donor because it is enolizable. There is 3 alpha hydrogen, so that is the reason that here first OH will be generated at this carbon, and then there will be removal of water, so CC double bond will be generated. So in this way we can work backward to derive the starting carbonyl compounds. You can also get this type of problem in exam. Okay, so if you find the video helpful, please like, share and subscribe. All the important links of playlist you can get in the description box. I'll meet you in the next video. Thank you for your time.